Hello everybody, welcome into another lesson. So today we are going to talk about Introduction to Series. Now, here you see several terms. You have 1 plus 3 over 1 plus 1 over 3 over 2. Sorry, 1 plus 3 times 1 plus 1 over 3 times 2 plus 1 over 3 times 3. Then it skips plus dot dot dot. And then plus the last term, 1 over 3 times 9. So what is a series? Well, instead of picturing these pluses, let's picture all these as commas, which would make this a sequence. A series simply takes the sequence and adds all terms together. In this case, you have a finite series because it starts at 1 and ends at 9. Alright, so we got that. Now, there are also infinite series where it'll go on infinitely, but we're not doing that yet. This is just finite because it starts at 1, stops at 9. So, how do we express that? How are we going to express that? We're not going to add this yet. We're just going to express it. So, how do we express a series? Well, don't let this scare you. When doing a series, we have what's called sigma. This is sigma. That is the Greek letter standing for a sum. Now, in general, it's going to be from your lower index of summation, n equals 1. That's called the index of summation. And then sum a sub n, and then it's going to go to some number, whether it's infinity or in this case 9. That number above the sigma notation is called your upper limit of summation. I'm just writing these terms out. Okay, so this weird looking symbol is called sigma. That is how we express a sum. This a sub n is really the sequence. You're taking the sum of every member of the sequence. That's what a series is. Instead of listing them, you're actually adding them together. That n equals 1 below the sigma is where the sequence starts. That's where you start adding the series. That's the index of summation. That number above the sigma is your upper limit of summation. So, how are we going to express that with this particular series? If you see pluses or minuses instead of commas, that denotes a series rather than a sequence. And now you're probably starting to see why we taught you sequences first, because they do tie into series. So, in this case, let's go ahead and figure out what the actual sequence is first. So we know we start with a sub n for a sequence. Now, look at your numerator. No matter what term it is, my numerator is 1. So a sub n equals 1 divided by, and then in the denominator we have a common 3. That much is a given. Now, what changes between each term is the number in the parentheses. You start at 1, you go all the way up to 9. So it's safe to say that a sub n would equal 1 over 3n. Depending upon what your term is, you're going to get a different answer. So we found the sequence, which is the first thing you want to do. Write the term for your sequence, because that's going to help you write out the series. To convert this to series notation, to sigma notation, you're going to take your sigma of your a sub n, which in this case is 1 over 3n, and then you're starting with an n equals 1, and then your upper limit, it goes from 1 to 9, so you would put the 9 above the sigma notation. So that is how we would express this sum in sigma notation. It means the exact same thing. So it's the sum from 1 to 9 of 1 over 3n. That's how you would express this particular series. All right, let's do a few more of these. Okay, let's see. So we have 5 over 1 plus 1 plus 5 over 1 plus 2 plus 5 over 1 plus 3 plus plus 5 over 1 plus 15. All right, so we have this series here, 5 over 1 plus 1 plus 5 over 1 plus 2 plus 5 over 1 plus 3. Then it skips all the way to 5 over 1 plus 15. So it actually stops at 5 over 1 plus 15. So first thing you want to do, because we have pluses, this denotes a series rather than a sequence. But the first thing we do is we take this as a sequence. We're going to find the formula for the explicit formula for the nth term of the sequence. So a sub n equals what? Well, you notice in every single term the numerator is 5, right? So you're going to have a 5 in your numerator. Now what about in your denominator? What's consistent in your denominator? You definitely have a 1 plus some number, right? So that'll be 5 over 1 plus, and it looks like it's just increasing by 1 every single term for the number to the right of the plus sign. So a sub n is going to equal 5 over 1 plus n. That's the formula for the sequence. Now we need to find the sum formula. So to find the sum, take your sigma notation. So there's your sigma of this a sub n. So that's going to be 5 over 1 plus n. And then you start at n equals 1. So that's your index of summation, n equals 1. And then it goes all the way to 15. Well, that's your upper limit of summation is 15. So you would put that above the sigma sign. So that is how you would express this sum in sigma notation. So it would be the sum from 1 to 15 of 5 over 1 plus n. That's how you would express this in sigma notation. All right, what about let's change it a bit. We have 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus minus 1 over 20 squared. Alright, so we have this particular series. We have 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus minus 1 over 20 squared where it stops. we need to definitely first, for this series, find the nth term of the sequence. Find a formula for the nth term of the sequence. Well, we start with our a sub n. Now, we definitely have a common 1 in the numerator, right? But here's one thing to consider. You go from alternating positive to negative to positive to negative and then finally negative. So every term alternates from positive to negative. So this is actually an alternating series. That means we have to account for that -1. So if the first term is positive, we can take -1 to the n minus 1, because -1 to the 1 minus 1 is -1 to the 0, which would end up giving us 1, positive 1. And if I did this with 2, for the second term, -1 to the 2 minus 1 is -1 to the first, which would give me a -1. And if I put in 3, I would get -1 to the second, which is a positive 1. So you see how the pattern goes. So we have a -1 to the n minus 1 power in the numerator. Now what about your denominator? It's just whatever term you're on to the second power. So the formula for the sequence is going to be a sub n equals -1 to the n minus 1 over n squared. Now that we found our sequence, we can go ahead and do the series. So set up your sigma notation. That's going to be the sum of this a sub n, which in this case is -1 to the n minus 1 all over n squared. We start at 1 for n. That's your index of summation. N equals 1. Your upper limit is 20 because it goes to 20. You'll put that above the sigma sign. So that is exactly how you would write this sum, this same thing here in sigma notation. The sum from 1 to 20 of -1 to the n minus 1 over n squared. Alright, let's do one more of these. And then we're going to work backwards. We have 1 over 4 plus 3 over 8 plus 7 over 16 plus 15 over 32 plus 31 over 64. And it actually stops there. It actually does stop there. So we have 1/4 plus 3/8 plus 7/16 plus 15 32nds plus 31 64ths. First thing we want to do is again find the formula for the sequence part of this. So a sub n equals what? If we notice the pattern here, so in the numerators you have 1, 3, 7, 15, and 31. Well, if we added one more to each of these, wouldn't that be a perfect 2 to a power? So in the numerator you're going to have 2 to the n power but minus 1. Alright, so let me explain here. If I took my n to be 1, 2 to the 1 is 2, minus 1 is 1. For my second term, 2 to the second is 4, minus 1 is 3. For my third term, 2 to the third is 8, minus 1 is 7. And you see how this just keeps building and building. So the numerator stands. What about our denominator? what about that denominator? So you have 4, 8, 16, 32, and 64. Well, keep in mind, we're starting where n equals 1, right? It's definitely 2 to the n, but if the first term yields a 4, the second yields an 8, the third yields a 16, that's actually going to be 2 to the n plus 1 power. Because 1 plus 1 is 2, 2 squared is 4, 2 plus 1 is 3, 2 to the third is 8, 3 plus 1 is 4, well, 2 to the fourth is 16, and you see how this builds in the denominator. So we found the formula for our sequence. Now, what about for our sum? So take your sigma notation. That's going to be of this a sub n, which would be 2 to the n minus 2 to the n, that whole 2 to the n quantity minus 1, all over 2 to the n plus 1 power. Now you're starting with an n equals 1, that's your index of summation. You go all the way to 5. That's your upper limit of summation. So that's how you would write this series in sigma notation. It would be the sum from 1 to 5 of 2 to the n, that quantity minus 1, all over 2 to the n plus 1 power. Alright, so that's converting these to sigma notation. Now, let's work backwards a bit here. We are actually going to go ahead and find the sum. So let's say we have this, the sum from I equals 1 to 5 of 2i plus 1. And we've been using n, but sometimes you'll see I, you'll see j, you'll see k, what have you. They all operate the same way. It doesn't matter what letter they pick. But when they use I in these sequences or in these series, they don't mean the imaginary number. They're just treating it like any other variable. So they don't mean square root of -1 for that. So how would you approach something like this to find the sum? Well, you're going to treat this again largely like you would a sequence at first. So it goes from 1 to 5, that means you need to find the first 5 terms of the sequence. So a sub 1 equals 2 times 1 plus 1. Well, that's going to be 2 plus 1, which is 3. Then find a sub 2, that's going to equal 2 times 2 plus 1, which would be 4 plus 1, which equals 5. A sub 3 equals 2 times 3 plus 1, which equals 6 plus 1, which is 7. A sub 4 equals 2 times 4 plus 1, which would be 8 plus 1, which equals 9. A sub 5 equals 2 times 5 plus 1, which would be 10 plus 1, which would be 11. Now that we found the first 5 terms, this is literally saying here that we're going to take all 5 of these terms, we're going to add them together. So that'd be 3 plus 5 plus 7 plus 9 plus 11. We're taking all 5 of those terms and going to add them together. Well, let's go ahead and do that. So 3 plus 5 is 8, plus 7 is 15, plus 9 is 24, plus 11 is 35. So this particular sum, once we add the first 5 terms together, would give you 35. All right. Now, what if you had something like this? the sum from k equals 1 to 4 of just 10. So you just have from k equals 1 to 4 of 10. You only have a constant. Well, there are a couple ways you can do this. If every term is 10, you're going from 1 to 4, you can just take 10 plus 10 plus 10 plus 10, right? Which we know would be 40. Also, in general, if you have a constant term, this only works for sums of constant terms, where n equals 1 to some constant term as your upper limit of summation of a constant. Now let's call that from z. Let's just say z for the upper limit. If you have the sum of a constant term from 1 to whatever, it's the same thing as taking your upper limit of summation times the constant. That does work for all constant term sums. That's assuming that n starts at 1. If not, it's going to change a little bit. But if n starts at 1, then you just take your upper limit of summation times the constant. You'll get the exact same thing. So let's see if we can find another one like this. Yeah, so we have the sum from k equals 1 to 6. Sorry, k equals 1 to 5 of the constant 6. Well, we just have the sum of a constant term. K starts at 1, the upper limit is 5, so all we have to do is take that upper limit of summation times the constant, and that would give you 30. So the sum of this series is going to be 30. Now, what about this? You have I equals 0 to 5 of 3i squared. So this time you're starting with the first number being 0 to 5. Well, you have to account for every single number. So what we're going to have to do here then is find those terms of the sequence. Since I starts at 0, we're actually going to have to take a sub 0. A sub 0 is going to be 3 times 0 squared, which is the same as 3 times 0, which would just give us 0, right? Alright, a sub 1, that's going to be 3 times 1 squared, which would just give us 3 times 1, which equals 3. A sub 2, that's going to be 3 times 2 squared, which is 3 times 4, that's 12. A sub 3 equals 3 times 3 squared, which is 3 times 9. That equals 27. We only got 2 more to do since we have to go to a sub 5. A sub 4 equals 3 times 4 squared. Well, that's going to be 3 times 16, which equals 48. Then we have a sub 5, which equals 3 times 5 squared. That's going to end up being 3 times 25, which equals 75. So what this sum is saying is that it's going to be from 0 to 5 of all these terms added together. So this is the same thing as taking 0 plus 3 plus 12 plus 27 plus 48 plus 75. And then we're actually going to add all 6 of these terms together. There are 6 terms because I started at 0. Okay, so let's add these together. 0 plus 3 plus 12 plus 27 plus 48 plus 75. That's going to give us a sum of 165. So the sum of this series would end up being 165 once we find all 6 terms of the sequence. And add them together, it's going to be 165. Let's see, we'll start from k equals 0 to 3 of 1 all over k squared plus 1. So we're taking the sum from k equals 0 to 3 of 1 over k squared plus 1. So notice we start at 0. We're actually going to have 4 terms we have to add together, right? Okay, so we need to start with a sub 0 since k starts at 0. That's 1 over 0 squared plus 1. Well, that equals 1 over 0 plus 1, which just gives you 1. 1 over 1 is 1. Okay, now a sub 1, that's going to equal 1 over 1 squared plus 1. Well, that equals 1 over 1 plus 1, or 1/2. Then a sub 2 equals 1 over 2 squared plus 1. So that's going to equal 1 over 4 plus 1, which would end up equaling 1/5. And then last but not least, let's find a sub 3. A sub 3 is going to equal 1 over 3 squared plus 1, which would equal 1 over 9 plus 1, which would give you 1/10. So now we found all 4 terms. We have all 4 of these terms. This is the same thing as taking that 1 plus that 1/2 plus that 1/5 plus that 1/10 and adding them all together. Well, we definitely need to get a common denominator, right? I think it's pretty safe to say our common denominator is going to be 10. So the first term, you multiply numerator and denominator by 10, you'll have 10 over 10 plus, we want to make the second denominator be a 10, so multiply everything by 5, so that would be plus 5/10 plus your 1/5, turn that into a denominator of 10, multiply everything by 2, that'll be plus 2/10. Then you just have plus that 1/10. Which when we add all this together, 10 plus 5 is 15, plus 2 is 17, plus 1 is 18. You'll have 18/10, which is the same thing as 9/5. So this particular series from 0 to 3 adds up to 9/5, or 1 4/5, however you prefer to think of it. Let's do one more of these, then we're going to do a few infinite series. Alright, so we have the sum from j equals 0 to 4 of -2 to the j power. Alright, so we have the sum from j equals 0 to 4 of -2 to the j power. Well, that negative indicates it's going to be an alternating series. So let's go ahead and find, since it starts at 0, we need to start at a sub 0 and go all the way to a sub 4, since the upper limit of summation is 4. So a sub 0 equals that -2 to the 0 power, which we know to be +1. Alright, now what is a sub 1? That's going to be -2 to the first power, which would end up giving you -2. A sub 2 is going to be -2 to the second power, which is going to be +4. Alright, then a sub 3 is going to end up being -2 to the third power, which is -8. And then a sub 4 equals -2 to the fourth power, which is +16. Now that we found all 5 of these terms from 0 to 4, this is the same thing as just taking all of those and adding them together. So we'll have 1 minus 2 plus 4 minus 8 plus 16. So we are just taking these 1 minus 2 plus 4 minus 8 plus 16 and adding them together. Well, alright, so 1 minus 2 is -1, plus 4 is +3, minus 8 is -5, plus 16, that's +11. So the sum of this series from 0 to 4 is going to be +11. Alright, now let's do a few infinite series. Because much like sequences can go to infinity, they can go on forever, so can a series. So let's say we go from I equals 1 to infinity of 5 times the quantity of 1/2 to the I power. So an infinite series is simply where infinity is your upper limit of summation rather than some finite number. Now, in a few lessons from now, we're going to talk about geometric series, where you can still get a finite answer for an infinite series under certain conditions with a geometric series. But for a lot of other types of series, they aren't going to have a finite sum because you're going to keep adding bigger and bigger and bigger numbers. If you can't arrive at a finite answer, that's called a divergent series. That means it diverges. It doesn't settle on one finite answer, but we'll get into that another time. Now, you may not be able to find an infinite sum, but you can take what's called a partial sum. What if they want the fourth partial sum? They want us to find the fourth partial sum of this. When you're taking a fourth partial sum or any partial sum, that changes your upper limit of summation. That's going to change your upper limit of summation to a 4 instead of infinity. So let's take I equals 1, and they tell us they want us to take the fourth partial sum. That's going to go from 1 to 4, since this is a partial sum of that 5 times 1/2 to the I power. Now all of a sudden this isn't so bad, since we're going from 1 to 4. Now we just take and find the first 4 terms. So a sub 1 is going to be 5 times 1/2 to the first power, which would just give you 5/2, right? A sub 1 is 5/2. Okay, what about a sub 2? That's going to be 5 times 1/2 to the second power, which would be 5 times 1/4, which would be 5/4. Alright, let's find a sub 3. That's going to equal 5 times 1/2 to the third power, which is going to equal 5 times 1/8, or simply 5/8. And then what about a sub 4? That's going to be 5 times 1/2 to the fourth power, which would end up equaling 5 times 1/16, or 5/16. So we found the first 4 terms. Now we can take the partial sum, the fourth partial sum. So just add these terms together. This is the same as taking that 5/2 plus the 5/4 plus the 5/8 plus the 5/16 and adding those together. So we definitely, I think it's safe to say, our common denominator needs to be 16, right? So for your first term, we have to multiply everything by 8. That would end up giving you 40/16. Plus your second term, that 5/4, you have to multiply everything by 4. That would be 20/16. Plus your third term, that 5/8, well, multiply everything by 2, you'll get 10/16. Plus you have a 5/16. Now just add all these together. 40 plus 20 is 60. Plus 10 is 70. Plus 5, well, that's 75/16. And that's actually the best we can do. It doesn't reduce any further. So the fourth partial sum of this infinite series, if you just go from 1 to 4, is 75/16. Well, let's do one more partial sum, and then we'll be done with the lesson. Alright, so we're going to go from I equals 1 to infinity of 2 times 1/3 to the I power. They want us to find the fifth partial sum. So initially this starts as another infinite series from I equals 1 to infinity of 2 times 1/3 to the I power. They want us just to find the fifth partial sum. Now, I will say, this is a geometric series that even with an infinite, doing an infinite series would converge to a finite answer. We actually could get a finite answer for this infinite series, but we're not doing that right now. So we're just going to go up to the fifth partial sum. So let's rewrite this sigma then, since we're only taking the fifth partial sum from I equals 1. We're going to make our upper limit of summation 5. Of this 2 times 1/3 to the I power. So that means we need to find the first 5 terms of a sequence, then add them together. So a sub 1 equals 2 times 1/3 to the first power. Well, that's just 2/3, right? Okay, now let's find our second term. A sub 2 equals 2 times 1/3 to the second power. That's going to equal 2 times 1/9, or simply 2/9. a sub 3, our third term, that's going to equal 2 times 1/3 to the third power. Well, that would give you 2 times 1/27th, or simply 2/27ths. Let's find the fourth term. A sub 4, that's going to be 2 times 1/3 to the fourth power. Well, that would be 2 times 1/81, or simply 2/81st. And then we have the fifth term. So a sub 5, that equals 2 times 1/3 to the fifth power. That's going to be 2 times 1/243, which would be 2/243. Now we've identified all 5 terms of the sequence part. That means we need to take every single one of them and add them together. So we're going to take that 2/3 plus that 2/9 plus that 2/27 plus that 2/81 plus that 2/243. We're going to add every single one of them together. Well, we definitely can see the common denominator is going to be 243. So for the first term, that 2/3, we're going to have to multiply everything by 81. You end up getting 162/243 plus, okay, now we need to take alright, so 2/9, we need to take that second term, multiply everything by 27. So 2 times 27 is 54 all over 243. Alright, and then we have that third term, the 2/27, so we just have to multiply everything by 9, so you'll end up getting 18 over 243. Plus your fourth term, the 2/81, just multiply everything by 3, you'll have 6 over 243. And then plus you have the 2 over 243. Just add them all together. Let's see what we get here. 162 plus 54 plus 18 plus 6 plus 2. That gives you 242 out of 243. So just a little bit south of 1. You have just a little less than 1. But the fifth partial sum of this series is going to be 242 divided by 243. Okay, so that's it for this lesson. Next lesson we're going to get into arithmetic sequences. So in this course we're going to talk about 2 main types of sequences in series, which are arithmetic and geometric. These past 2 lessons have just been an introduction, which have had all kinds of sequences in series. In pre-calculus here, we don't quite have the calculus tools and all those other tools yet to evaluate other types of series, but we can certainly do arithmetic and geometric series. All the other types come in calculus 2 and even later. So I hope everyone has a great day. Take care.
Imagine being able to build an app with your name on it just by...
Sorry guys, stupid notification.